Hello everyone, welcome to the 15th episode of Deep Learning with Pytorch series. So finally, we are building a neural network with Pytorch. So after all the groundwork, starting from very scratch to the going through all the things that are required for you to build a neural network in the last 14 episodes. And also finally in the 15th episode, we are starting ahead with a building a PyTorch neural network module. So we will build the neural network using PyTorch on a MNIST dataset. So this is MNIST kind of a hello world for any deep learning task which you want to do. So here we generally have 10 labels. So these are handwritten digits. So features are like numerical representation of an image where each of the features are kind of a pixel value. So the image is of a 28 cross 28 image where each of the values are pixel values. And for each image, we have a label. So these labels are nothing but what is that image actually contains, starting from 0 to 9. Only one of the digits of this 0 to 9 would be the label of your data set, right? Okay, now let's get started. So with this NN dot module, we will try to build the PyTorch model. And this is kind of the base class for all neural network modules. And our model should always subclass this class. So we will see this example when we are building the neural network, we will subclass this NN dot module, right? Then we will use other functionalities of PyTorch, like Optim is also a utility package through which we will do the optimization. So as I mentioned, like we will do the subclass of this NN dot module, and that will also help us to keep track of the state of while building the model, right? And NN dot module has several other attributes or methods like dot parameters, zero grad. So using all these attributes and methods, we will use that to efficiently build a neural network using PyTorch, right? So at first, we need to do a data preprocessing step. So the data set which we are working on, as I mentioned, that is MNIST. So the very basic few steps is we will import this Torch library and also from Torch Vision. So this Torch Vision is a PyTorch library which are related to computer vision. And there are a lot of data sets which are freely available. And that is MNIST is one of them. So we will import that. And once we imported that, what we will do is we will transform that data set using this transforms component, right, or method. So here we are doing a series of transformations on top of our data. At first, we are converting this data to torch tensor. Then we are normalizing the data. So normalizing means every image or every features which we have. So using a global mean, which is like 0.1307 and a standard deviation of 0.3081. With this global mean and standard deviation, we will normalize our features so that it is the features are kind of normalized, right? So once we do that, like we created the transform, then using that transform, we will do the we will download the data. So this is the way to download the data. Like for the first time, it will download the full data set into your local system. But if you run it again, it will not do the download. It will just fetch from your local system, right? So I am just downloading the train data set. So slowly we will move to the concept of test and validation data set. So for now, we are just building a neural network using the train data set, right? So in case you are wondering and you just dropped into this video and why we are not using a test data set or a validation data set. So this is just that we are beginning building a PyTorch neural network. So we will just see how the training process works. So in the future videos, we will see how we can measure the overfitting and other criteria using a test or a validation set, right? So yeah, train equals to true, then download equals to true, and the transform which we created in the previous step that we are providing here. So after that, we are checking the shape of my data set. So there are around 60,000 rows or samples which are there in our training data set. After that, what we will create is we will create data loaders, right? So using this data loader, we will create batches of data or mini batches of our whole input data. And on top of that, we will train our model, right? So if you are not aware of this data set and data loader concept, please refer to my earlier video where I have shown you what is the concept of data set and data loader, right? So once we create a data loader, there also we mention the batch size. So batch size here is 50, and number of workers are nothing but number of sub processes to use for data loading, right? So currently, as we are not dealing with huge data, we are just making it as 0. So once we create the data loader, the first thing would be to check one of the batches, right? So I'm just creating a data iterator and just fetching the images and level corresponding to that. So you will see the shape of my image is because the batch size is 50. So this 50 is coming up here, and this is the shape of my image, right? So it's a black and white image. So only one channel we have. So channel is what we will talk in detail when we go to the computer vision part of this tutorial series. So here, just imagine that we are working with black and white images. So only one channel is there, and it's a 28 cross 28 image. And also the label is also for 50 images, we have 50 labels corresponding to that. Okay, so now we just picked up one images out of this batch, which is the second image, which I am accessing by images within third bracket equals to 1. And then at first I'm converting it to NumPy because the data is already in a tensor format, right? So to work with matplotlib, we need to convert it to first NumPy, then squeeze and do the other operations to visualize the data. So once we have that, we will also storing this image or this feature into this image 0 variable. So this we will later on see how the model is performing on this specific training example, and we will do that once the model is trained, right? Okay, now, so as I mentioned, like our images are nothing but 28 cross 28 shape of image, but we cannot pass this data to my neural network model. We need to reshape and create a vector out of it, which is kind of a stretched out vector as I have shown here. So like this will be stretched out and it will be converted to a shape of this, right? And for a particular batch, the shape will be like batch size and the number of features. Here, the number of features are nothing but 1 cross 28 cross 28, which is nothing but 784, right? So why I am saying 1 cross 28 cross 28? Because that is the shape of a single image, right? So using that, we will kind of create a flat tensor, which will be a shape of 784, and we will pass this to our model, right? Okay, so then let's go and see the model architecture, right? How we will create the model architecture. So this NN, right? As I mentioned, like NN dot module is the base module for every neural network in Pytorch. So we will subclass this and we will create a new class out of it. So once we create that, like layer initialization or layer definitions, we will be doing inside the constructor, which is nothing but the init method, right? Here, the input dimensions are 784 because we are like converting the images to a flattened vector, and then we are passing it to the neural network, right? So there would be 784 dimensions in the input layer, and we are creating a hidden layer, and that hidden layer shape is 256, right? And then using this 256, we will create output layer, which is like the because we have 10 classes, so the output layer shape would be 10, right? Now, how we define this NN dot layer is the syntax is the input size and the output size. So for the FC1, the input size is 784 and the output shape is 256. For FC2 or the feed forward layer, second layers of linear layer shape is 256 is the input number of nodes and 10 is the output nodes. And inside the forward function, we will do the steps that should be same as forward propagation, right? So at first we are just flattening out this input image to this 784 stretched out vector. Then we are passing it through the first fully connected layer, and then we are using a ReLU. So we are just using an activation function on top of the linear operation. So this is the linear operation, right? So after that, we are using f.relu to get the activation output of this layer. And then we kind of pass this X to the next layer, which is the fully connected layer 2. And we get the final output, which we return from forward method, right? So this is how we generally create a class. And this class is basically the structure of my neural networks. Now, if you just want to visualize, your X is nothing but the input features, which has a shape of 784. And in the hidden layer, we have 256 nodes. So there we have like each of the nodes will be connected to another node of the next layer. And in the output layer, we have 10 neurons because we are doing multi-class classification where we have 10 levels, right? So this is how you can visualize the model architecture. Now, once the model is created, we can just create an object out of this class, and that we will use in the downstream process. So after that, the next steps is to define the loss function and also the optimizer, right? So we are using this cross entropy loss. So if you remember from my previous session, so in case of PyTorch, the cross entropy loss incorporates your log softmax and also the negative log likelihood loss, right? So that's why as we do not have a softmax at the output layer, so we can use this cross entropy loss as a loss function, right? And we are using a stochastic gradient descent where we are passing the model parameters along with the learning rate. So this is how you define your model and also your loss function and also your optimizer. So generally in PyTorch, we denote the loss function with criteria, right? Okay, so there are several other optimizers are which also present like Adam, RMS Prop, SGD, and AdaGrad, right? So in case you are not familiar with this, I have a detailed video on this all this topic. So the link of that is also will be present in this notebook that you can refer, right? Now we will start the model training process, right? So in the model training process, we are doing 10 epochs. So if you remember, epoch is like a full pass through all the training examples. So we divide our data to small batches, small mini batches, and on top of that, we will do multiple iterations on the full data set. And and on that, we will measure the training loss. So we will do 10 epochs. So what we are doing is we are looping through our train loader, which is nothing but we created using the data loader method. And then we are just getting our data and target. So at first we need to zero out the gradients, right? So PyTorch, by default, like PyTorch accumulates the gradient of the previous step. So in case we do not zero out the gradients, so previous iterations gradients will be accumulated with the current iterations gradients. So that's why using this zero grad, we will clear out the gradients, and this we should do before doing the backward method, right? Then we using the model, we will pass through our data and we will get the output. So that is kind of the forward propagation step, right? So this is the forward propagation step. So once we have the output, we will compare my output with the actual label or the target, and we will calculate the loss. So this is where the loss calculations are happening, right? So once the loss is calculated, we will do this loss dot backward, which will calculate the gradients using the PyTorch autograd method, and it will store the gradients, right? Once the gradient is calculated, then it will do a weight optimization using this optimizer dot step, right? So optimizer dot step, it will just optimize the weights using the gradient calculated using this backward method, right? Where we are doing the backward propagation. So and every iteration we are kind of we are appending the loss. So we will monitor how the loss is decreasing with number of increasing epochs, right? So you can see like we started with a loss of 0.51, then in the end our loss is around 0.099 something, right? So we can see like the loss is getting decreased with the number of epochs. So that is one of the indication that your model is getting trained well, right? So just to reiterate again, we loop through our train loader, then we zero out the gradients, which will avoid the gradient accumulation. Then we pass our data through the model to get the output. Once we have the output, we calculate the loss. Once we have the loss, we calculate the gradients. Once we have the gradients, we do the weight optimization, right? So yeah, so this is how it works. So after that, your model will be trained, right? So now here I have used the loss function as cross entropy loss, right? Now we also have this negative log likelihood loss, which does not include the log softmax, right? So if you define, if you want to use the negative log likelihood loss, what you need to do is in the last layer, in the output layer, you need to have a log softmax, right? So that I have used here. And again, I did the same steps and also created. So here, if you see, I have used the negative log likelihood, and it can work only if you have the log softmax at the output layer. And after that, similarly, I'm just monitoring my loss. So once the model is trained, then we can make predictions, right? So we will. So if you remember, like we stored image feature in this image zero variable. So we will pass this through our model and we will get the log probabilities, right? So once we get this log probabilities or the output of my softmax, as we are using a log softmax, so there is a log associated with this model architecture of Pytorch. So we need to take the exponent torch.exp to get back into the original range, right? So once we have that, we have the output looks like this. So we have 10 nodes. So we will have 10 nodes at the output layer. So we will get 10 outputs, and the shape of a single prediction would be 1 cross 10 because we will have 10 nodes and because we have 10 labels in our data set, right? So how we will fetch the most probable one, right? Most probable class, right? So we will use this top k method, which comes from Pytorch. So and we are asking Pytorch to fetch only the highest probable method, highest probable class along with the probability of that. So this top p is nothing but the probability associated with that, and this top class is nothing but the index where the highest probability is associated, which is in turn is the class, right? So here, if you see, if I just go back to the prediction of this, so here you see these are the output of from my PS, right, or the probability from my model. So here the highest value is located here, right? So rest of the values are lesser than this. So if you use a top k, it will only fetch this value, and as it is located to the 0th index, so it will also give you that index value, which is 0, and which in turn we can say it is a class 0, or the prediction is associated with 0 handwritten digit, right? So yeah, this is the way to do it. Now we can check. Now we can check accuracy on a particular batch, right? So this is a batch where we have 50 number of records. So we pass that batch through our model and we get log PS. Then we take this torch.exp to get back into the normal range, and after that, using this top k, we can fetch this top p and top class, right? So these are like the shape of each of this would be 50 each, right? And so here I'm just printing the top 10 predictions or top 10 examples from that particular batch, and these are the classes associated with that, right? So you'll see the shape of this is like 50 comma 1 for class, and for labels it's just 50, right? So once we have our predicted values, so we can compare this labels with the actual value, right? So and which is actual value is nothing but the top class, right? So top class sorry, top class is the predicted value, and our labels is the actual value, right? So, but before doing that, you need to be careful that the shape of this top class is 50 comma 1, which is a 2D tensor, right? But your label is of shape of 50, which is a one-dimensional tensor. So I'm just converting this labels as the same shape of my top class using this command, right? And then I'm just equating these two to calculate this variable, which is equals. And this is how the equals look like, right? Now, using this equal, if you just calculate the mean, it will give you the accuracy, right? Which will tell you what is the average number of correct predictions in this batch, right? But if you straight away use this method, it will throw certain error because your equals is not a float tensor, and this torch dot mean expects your equal to be a float tensor, right? So we are just converting this equals to float tensor, and then we are calculating the accuracy, right? And in the end, we will we can see that the for this particular batch, the accuracy is 93 or 94%, we can say, right? So this is how we train a neural network using a PyTorch concept and a PyTorch class, where we kind of create a model using PyTorch NN dot module, and using like a loss function and a optimizer, we can like train the model, and finally we can check the accuracies or the performance of my model. So I hope this video is useful to you and you kind of get the concept. And slowly from the next video onwards, we will try to improvise the results. Like we bring in the test set and the validation set, and we will like see if there is any overfitting going on or not. And if there is any overfitting going on, how we can tackle those overfittings. So slowly we will build those concepts also. So I hope you like this series and also for this particular video. Stay tuned for further updates, and please don't forget to subscribe this channel for more updates. Thank you all.